here is the situation for what we call motional EMF. And there's a couple different ways to look at this motional EMF stuff, and I can help you understand that. What we have right here is a magnetic field, a uniform magnetic field in a region, and this magnetic field is going into the screen right here. We have a bar, a conducting bar, that is moving at speed v to the right. So let's pick up where we ended up last time. What I want you to do is figure out which way are the forces on the electrons and on the positive charges in this bar as it moves to the right. Hint, the velocities of all these charges is to the right. So you can start off with the positive charges. Which way will they be forced as you drag this bar right here to the right? Go ahead and use your force on a charge right-hand rule. Figure that out. So I've got V to the right. I've got B into the page. That means I've got to like bend my fingers that away. And the force on the positive charge will be up. So these positive charges, they move upward like this. Let me get another color. Positive charges move upward. Those positives get pushed upward. The negatives, you can use your left-hand rule or just use the opposite logic. Which way will the negative charges get forced? Down. So our negative charges are forced down to the bottom of this. So what happens is we end up with a whole bunch of positive charges up here, a whole bunch of negative charges up here. I want you to point in the direction of the electric field that separation of charge causes. Point in the direction of the electric field inside this bar, and there is one. Go ahead and point in that direction. Please point in that direction and put your Chromebooks away if you cannot focus on this lecture. Okay, what direction? Antra, what do you say? What's the direction of the electric field?
Down.
It is down towards the bottom because here's the positives. Our electric field points down that way. That is the E field. So we've got the force on those charges is QVB rather. The magnetic force on those charges is QVB. Notice that there is an electric force on the charges. These are trying to attract together, and that force is QE. When we keep moving this to the right, those two forces are equal because the charges stop moving. Hence, we just set QE, which is the electric force. It's balanced by QVB. Otherwise, the charges would be moving. We can get rid of the Q's right here. And what we have is the electric field is equal to V, the velocity, times B. So what we get is the delta V. There's a voltage difference between the top and the bottom. The voltage difference is just negative ed you could use. The magnitude is E times L. This is length L. I should have mentioned that. So you can use delta V is negative ed, and our distance is L. So our voltage difference magnitude is E times L. Electric field E, L. But according to this, you put that in there and you get our delta V. And here's our bottom line. The voltage difference across from top to bottom of this thing is BLV. B is the magnetic field strength. L is the length of the rod. V is its velocity. We use the force on a moving charge right-hand rule to figure that out. By the way, I should indicate before I go on, I want to indicate right here, this is really negative ed, and that's why this is really negative BLV, but what we're getting is just the magnitude BLV in that situation. With Faraday's law, you can figure out the same thing, but in this situation, what we have right here is we have our bar that we're moving through the field right over here. Here's the bar we're moving through the field, the conductor. It is on two conducting rails. So, and this is a resistor. So unlike the situation we just had, we're actually going to get current flowing here. Here's how we can use this Faraday's law to figure out the very same thing. The EMF is equal to the negative rate of change of magnetic flux. what is the magnetic flux? Let's review that. Magnetic flux is what dotted on what? B dotted on A, or the integral of B dotted on dA. Luckily, this is just a constant B field. The A, though, is changing. So let's see if we can get an expression for A here. Let's go ahead and do this right up here. The flux is B dot A. Notice that that is just going to be B, magnetic field, times L, the length of this conducting bar right there, times X, how far it is away from our 0 point right there. We're just going to call that X, the distance that the bar is away from X equals 0. So our area is area is L, this length right there, that's L, times X, the distance away from the point that I've called X equals 0. So that is our flux is BLX. To find the negative rate of change of that, it's negative d dt right there times our flux, BLX. Only one of these is not a constant. Which one of these is not a constant? X is not a constant. So everything else we can bring out. We can bring out B and L. It's negative BL. What is the time rate of change of just X? Yeah, it's just your velocity. So we have just found the EMF by Faraday's law. Same thing, negative BLV. That negative means it's going to try to keep the flux the same. Here's what I want you to do. I want you to use Lenz's law to figure out, is the current going clockwise in this loop or counterclockwise? When I move this bar right here, when I move it that way, is this amount of flux going to get bigger or smaller when I move the bar to the right? It's going to get bigger, so do I start my thumb short or long? I'm going to start it short. Our magnetic field is into the page. It starts off small. You will lengthen your thumb because we're getting more flux into the page. So that is the change is that way. Nature wants to oppose that, so the opposing the change is towards out of the screen. And then the current that will be necessary to keep that flux about the same will be counterclockwise. So this is the way the current's going. Up that way, there's I. This way, I. And down through there is I. And that way is I. So we have a counterclockwise current using Faraday's law. That negative sign is because it tries to reduce the amount of change in magnetic flux.